Hello, everyone, and welcome to today's webinar. My name is Jennifer Caveney, and I will be facilitating today's presentation. I would like to begin by introducing Trish Hook, who will be moderating today's presentation. Trish earned her bachelor's degree in product development from the London Institute. After a long tenure as a director in the events industry, she joined Eurofins in 2021, specializing in global compliance, packaging, food contact materials, and failure mechanisms. With a diverse client base and cross-industry experience, Trish brings a strategic approach to product safety and regulatory navigation. Trish, I'll hand it over to you.
Thanks, Jen. Hi, everybody. Thank you so much for taking the time to join us today for our webinar. As she mentioned, we're here today to discuss migration studies in support of the FDA Food Content Notification, or FCN. As Jen mentioned, I am Trish Hook. I am the Business Development Strategy and Solutions Manager for SFA. My role is to support customers by providing tailored food contact material services, monitoring regulatory updates, and identifying solutions to help maintain compliance for your product safety. I'm joined by Drew Dumas. Drew has been with Eurofins for 11 years. He holds a bachelor degree in biochemistry from the University of Missouri, and he has an extensive background in chemistry, as well as being well-versed in global, federal, state regulations with a focus on food contact materials. He will be guiding us through today's presentation, bringing a broad depth of knowledge and insight into the subject. So who are we? We are the SFA analytical group of Eurofins. That includes 5 labs, which is SF Analytical, that's us today. We've got GMP Microbiology in Horsham, Pennsylvania, Eurofins Craft, Animal Health, and SN Special Analysis and Testing. What we do is we bring a non-routine, think outside the box approach to projects, covering anything from food and beverage, medical, cosmetics, consumer products, and much, much more. As you can see here from the map, there we are, we're in New Berlin, and our other locations spread very evenly across the country. In our group, these are specializing in our services. We use a variety of lab techniques such as GC, LC, FTIR, DSC, particle size analysis, and we cover a really broad range of testing subjects such as foreign material ID, chemical analysis, custom investigation, off flavor, off odor, root cause, and so on and so forth. And now I'm going to hand it over to Drew, who's going to walk you through this topic in much more detail.
All right, thank you, Trish. Lovely introduction. I think that's probably one of the only reasons why I like doing a webinar, is just for a little bit of a ego scratch or boost there. Thank you. So yeah, today, what we're going to talk about is a little bit on the migration testing and how we can help supplement or help with your food contact notification process. I think first and foremost, it's going to be important to give you an overview of the regulatory framework here in the US, based on what the FDA, or based on what Congress has legislated and the FDA has implemented in terms of regulations. We'll also talk about some, how to perform migration assessments, which, can either be done through calculations, diffusion modeling, or through analytical testing. I'd like to also kind of mention that we'll get into what the difference really is between intentional and non-intentional added substances. You may have heard this term NIAS before. It's ever evolving, but really it's going to be important in terms of today's analysis, and especially when it comes to the risk of using recycled materials and evaluating their purity, as well as understanding the quality to meet not only regulations, but also keeping product, the food product safe, stable over the course of its shelf life. And then we'll go into a small discussion really with safety evaluations, how we determine, once we have a migration calculation, what that does in terms of, estimated daily intakes or cumulative estimated daily intakes, and how those are compared to ADIs. So in saying that, brief history. I know it's probably the most boring part to talk about, but it is one of the most important pieces to talk about, because really this gives you the scope and the overlay of how things work. I think when you're talking about food contact materials, these were first regulated after Congress enacted the Food Additive Amendment to the FD&C Act. Direct and indirect food additives were born out of this amendment. So this gave rise to the 21 CFR regulations that most of you may be knowledgeable about, again, imposed by the FDA. It also brought about what's called the Food Additive Petition, or FAP, process for evaluating and authorizing substances and materials. Since this process can take years for any particular single substance, and resource time, obviously, to evaluate all the necessary information and data that goes into an FAP. In 1995, the FDA issued a ruling, called the Threshold Regulation Rule, to allow for manufacturers to streamline the FDA review process and minimize, resources for, what can probably considered lower risk substances, anything that really has a dietary concentration exposure of less than 0.5 parts per billion. And then in 1997, Congress passed in the FDA Modernization Act a streamlined means for the FDA to evaluate safety of substances for their intended uses. This was referred to as the food contact notification process, and really is today the primary method for authorizing new uses, FCSs. Not to say you can't do that through a food additive petition process, however, again, lengthy and time consuming. So the FCN process is that primary method. All three of these means are ways of authorizing, or have their own authorization list, in a sense, on the FDA's website, into what are called inventories or databases of substances of authorized use. So those can all be found on the database. Here is more of a breakout of the FDA regulatory framework. Again, going back to those 21 CFRs, it's kind of broken down, as you can see, in terms of packaging applications, whether it's for paper or paperboard. There are specific sections on 177 is for polymers. Different attributes, 175 for things like coatings or adhesives. So it's broken out into sections on not only from packaging applications, but also in specific polymers. So you may have certain subchapters that identify, for example, here's 1520 for polyolefins like HDPE or polypropylene. You may have polyethylene terephthalate, or PET, that's regulated under 177.1630. So again, identifying that all these have different means to them. They're not just a cap or a catch-all. There may be cross references to specific ones that you may need to take into account when defining your authorization, or making sure that you are all the materials and substances are authorized for its use. Yeah. Also, there is the GRAS status, or what is called generally recognized as safe. There is a regulation for this, or a GRAS notice regulation under 182, or one of those subchapters of the Code of Federal Regulations anyway. However, there is a database listing these notices as well. Also, GRAS is a self-assessment or a self-determination in a sense. So manufacturers can determine their substances aren't carcinogenic, mutagenic, or reproductive toxins. How if they fit below a certain EDI, or their EDI fits below a certain acceptable daily intake. So anyway, this actually, the GRAS status has been kind of really subjected to scrutiny over the years, and more so recently. And I do want to just say, as of May 15th, I believe the DHS is now having the FDA, the CFSA and department actually review many of these GROS notices for particular food additives and indirect food additives. We'll get into more of what that means later, but right now that's something that we're paying close attention to in terms of how they're evaluating GROS status. Also, part of the regulatory framework is any prior sanctioned letters. Prior to 1958, there were many letters written by the toxicologists of the FDA, basically authorizing safe use of certain substances. There was also letters written after 1958, so the problem is trying to find all that information in that data, because those could be as easily packed away in some cabinet or drawer somewhere where it's not really made public. However, there is a prior sanction section. I believe that is 21 CFR 182 that is in the CFR. And lastly, what we had just talked about, the other two means for authorization is threshold regulation and the FCN process. I will say that really kind of the differences between the two here are one is going to be based on, or one is very proprietary to a manufacturer, specifically the FCN process, whereas a threshold regulation, any manufacturer of the substance or article that uses that substance can utilize that TOR. Then we have really kind of, I think it's important that you understand what it means by adulteration of food. I think food and packaging supply chains, anywhere from raw material suppliers, converters, manufacturers of finished product, even those companies that transport finished food and packaging downstream, share a common responsibility really to ensure that the food does not become adulterated at each stage of the life cycle of the food and its packaging. The adulteration clause for food contact materials is implemented under 21 CFR 174.5, and really it basically states the materials need to be of a suitable purity for their intended use. Ways in which food contact materials may adulterate food are: one, the material component releases poisonous or deleterious substances, injuring or rendering it injurious to health, human health. The material or component renders the food unfit for human consumption, either by imparting off odor or taste, or the component qualifies as a food additive and is not subject to pre-market clearance by the FDA. We'll get more into that and how no migration assumptions can be utilized or clearances. So I think it's very important to understand the terminology, as this will really kind of define the scope and what you're including in terms of what is an FCS or what is an indirect food additive, and when you maybe use migration testing or calculations to kind of understand if what you have in terms of what has propensity to leach into foods. So anyway, saying that, a food contact substance is defined as any substance that is intended for use as a component of materials used in manufacturing, packaging, transporting, or holding food, if such use is not intended to have a technical effect in such food. So it's very important to understand that a food contact substance in itself is part of what would be basically in contact with the food and defining what a food contact material is here in the US. Food additives. Here we have a definition that comes directly from the FD&C Act. They are all substances which result or may reasonably be expected to result directly or indirectly, which is kind of where it comes from the packaging side of things, either in their becoming a component of food or otherwise affecting the characteristics of food. There's also a subclause within the food additive definition that states if there is no migration of a packaging component from the package to the food, it does not become a component of the food and thus is not a food additive. This is important because then if the pre-market clearance of an FCS is only required when it's deemed a food additive. Therefore, if you have an FCS in a packaging and it does not migrate, then it is not considered a food additive and now does not have any pre-market clearance necessary for its use. So why should we be concerned? Well, regulations, right? There's more of those and revisions to these happening all over the world. Anywhere from EU to Mercosur. China, they have very similar requirements in terms of SML limits and OML requirements, and what's required for those limits, specific standards that need to be followed. Also, again, like we were saying, what we're talking about here today is for the food contact notification or a threshold of regulation notification to the FDA. It's important to understand the risks that are associated with using materials and the any indirect food additives. So migrants can certainly impact food in several different ways, and two of those ways which really are of most important is the food safety. We want to make sure that there's nothing harmful that migrates, at least at concentrations that would deem it harmful for human consumption. Also, food quality. We don't want to impart any color, off odor, or taste, changing those organoleptic properties. So, a lot of times you may want to perform sensory analysis, evaluations to understand its fit for purpose. In demonstrating regulatory compliance, really it involves 5 key aspects. I think it's important to understand that most of the time in all of these regulations, there is a listing of substances on positive lists. Take the 21 CFR or FDA, for example, really it's yes, like you go back to the 1520 for polyolefins, there's also a list of other antioxidants and other additives that could be used at maybe certain limitations of use, residual levels that could be found in there. So there's already an authorized process and understanding of that these particular materials and substances can be used. So that's important to look there first. Understanding byproducts and residuals that are controlled within safe levels. Obviously, this goes back to the purity of the raw materials that you're using in those packaging products. Any degradation products from normal use must be assessed. So if obviously if the polymer is not meant to be used at high temperatures, you may actually get excipient or some of the polymer to actually degrade and leach into those foods, and many of those oligomer products in a sense that would be of concern, at least less than that 1,000 Dalton level. Also, adequate control of product purity. Again, just ensuring that you don't have anything in terms of those impurities that would render it unsafe for consumption. And then just having a specific quality management system in place for adequate controls. Again, whether that's for virgin material suppliers, recycled material suppliers, converters of those materials, all the way to the food manufacturers themselves. Just understanding that you have a quality management system and you're keeping controls in place. So that brings us to what is migration. I think this is very important to understand in a sense, because really in the context of food contact materials, migration means it's the transfer of substances from packaging materials into food, basically. I would say that migrating substances can potentially come from packaging substrates. For example, paper, board, plastic, as well as even the packaging components. If you have a multi-layer film, it could be coming from the adhesives and penetrating through the barrier layers, possibly printing inks, whether that through permeation or through set-off, or coatings, to make up the overall packaging. So really, I think it's important to consider the overall packaging material article in a sense, not just the direct food contact piece of it. There are many ways in which migration can occur, and I kind of mentioned a couple here. Contact direct migration, or the transfer of the surface from gas phase, or from the surface directly. Gas phase migration, which is the transfer through air by the process of diffusion. Penetration, or what's called through migration, is the transfer of non-food contact side to the food contact side, or through the layers to the food contact side. And then set-off migration, again, would be from a non-food contact side in stackable items, or say rolls or reams that have pressure applied to the food contact side, and then food applied to that as in terms of diffusion onto the surface. Migration assessments can be used to establish a status for uncleared substances. Obviously, they can also be used to prepare an FCN or TOR to establish a no migration self-determination. No migration really kind of means in terms of a concentration limits. The Ramsey proposal was provided at less than 50 parts per billion, back in the day. That could be less than 10 parts per billion though in high consumption cases. And then obviously if it's a CMR, really in terms of purities, you need to make sure that those are very of low risk and safety factors are involved. No migration can be determined through calculations like worst case calculations, assuming 100% of the residual amount in the material obviously will transfer to the food, or through modeling calculations using diffusion kinetics as shown here. And then lastly, obviously, analytical testing can obviously be performed as well. Migration is diffusive, meaning there is a net movement of the substances from a higher concentration to a lower concentration until equilibrium is established. And when performing tests, we obviously see many times that equilibrium is met prior to even getting to the final time point at which the migration study is conducted. So this is always establishes kind of what is worst case in a sense. So there are many factors that I wanted to highlight here that contribute to chemical migration. I think it's important to understand what these factors are. The composition of the material and contact with food is important to understand. Different materials differ in their permeability to potential migrants. Glass and metal materials really are kind of, they just leach, elemental material or elements into those simulants or food. However, they're really kind of considered an absolute barrier points as well. Plastics made of different polymers, even thicknesses or density, will have impacts on the rate of migration. So these are all very important considerations in understanding, how migrants may transfer into food. The nature and extent of contact with the food is also very important. Compatibility of the materials with food and the solubility in those foods. I think foods, that are liquids tend to elicit more of a transfer than solids, right? You have polar and non-polar migrants that really, when you have polar migrants, they're going to transfer to a polar stimulant like water or a low ethanolic solution. You might have non-polar stimulants like isooctane or hexanes or olive oil that is utilized to simulate a non-polar compounds that would transfer into them. Also, high surface area foods are more susceptible to migration potential. So that's, something also to keep in consideration. Increase in temperature and extended storage times to meet shelf stability will also increase the potential of migrants into food. Also, smaller molecule size, such as additives, will diffuse through materials to a greater extent than, say, larger compounds such as, oligomer fractions and so on and so forth. Here, I have just a short, quick guide on, how to kind of think of migration in a sense, in terms of transfer, when you're trying to identify, okay, well, should I use a larger container versus a smaller container? What's worse contact time and temperature going to do in terms of, the propensity? What type of food stuff is in contact with my food to understand how aggressive it would be for that particular material? And here we have basically a calculation. I think it's important to kind of understand in terms of worst case calculation. Obviously, this is for plastics, but this obviously can be changed for certain printing inks, coatings, multi-layer films even. As long as you know certain parameters, you can actually perform these fairly easily and simple. And it'll give you a basis on trying to identify, if migration analysis is absolutely needed in certain cases. And we can always help with this as well in terms of performing calculations. But I think the important piece here is really, understanding, if you look at this, if I look at this and say, well, okay, I have a smaller container, of surface area, but I also have many forms and or many volumes that can be filled. What would be worst case scenario? And typically, usually when you increase the volume of food or the mass weight of food, obviously that's going to decrease the concentration and vice versa with surface area. Same goes with thickness and density. If you have like a plastic with a thicker density or sorry, a larger density and thicker, you're going to have more propensity of a surface area that's involved with that food for more migrants to be there in terms of the concentration residual level. So all things to consider and think about when you're determining if migration is even analysis is even necessary. And here is, I think a really good overview of designing a migration study. We at Eurofins have questionnaires, and this is the reason why we have our clients fill out questionnaires, is to really understand everything that's needed in order to perform, everything to make sure that that packaging is suitable for its final use. Number one, chemical identity of a food contact substance. Obviously, any possible degradation products or impurities are going to be important. Identifying if the substance is an article in itself or a component, or used in the production of an article or component, right? And maybe it's a production aid or something along those lines. And also details on the manufacturing process, including raw materials, catalysts used, production aids, possible side reactions. These are all very important to understand, what NIAS would be considered in there, and try to formulate more of a known intentional degree of targeted analysis at that point, instead of always looking for unknowns and what will try to make the process a little bit less difficult on the analyst in a sense. I think knowing the intended use will help in making the material that would be used in the study as a worst case exposure scenario important. This might include maximizing the concentration of the additive, if that's the case, possibly the thickness of the polymer at worst case, and the use of additives to facilitate maybe an increased migration potential, maybe such as like plasticizers. If you expect different degrees of concentration of plasticizer being in there, and that's not the food contact substance that you're getting authorization for, obviously anything that's going to allow that free flow is going to impact the design of the study. So we'd want to make sure that you formulate the test article in a way that facilitates worst case scenarios. Testing of conditions of single use versus repeated use articles are quite different. Instead of exposing the article or component to multiple cycles under the same conditions, the FDA recommended protocol really is to make sure that you test at the worst case temperature over the course of that 10 days. That way you can extrapolate that migration data and calculate an exposure over the surface life of a product. So just identifying between single use versus repeated use, they may have actual different protocol recommendations. And then also it's important to simulate as close as possible real life surface area to volume ratios. However, the FDA does have a default assumption of what's considered surface, the food to surface area ratio of 10 grams per square inch. And we can normally, test to that or meet those conditions when designing the study. Here we have the different food simulants and test conditions that can be utilized. Again, this is not an exhaustive list by any means, but it does give you a degree or understanding of what can be used. There is a table, obviously, that fits under 21 CFR 176.170. Those conditions, however, are very different in a sense of, because those are meant for total non-volatile extractive tests or quality characterizations, not migration tests. But it does provide you with a degree of what food types to consider, what is considered aqueous and acidic, what is considered low or high alcoholic foods, and what stimulants to use. Fatty foods, how are you going to simulate those? If you're using a food type oil or a synthetic, triglyceride like HB307. So it's very important in understanding, what food stimulants to use based on the food types that you expect to come into contact. Obviously, there's also different testing conditions in terms of time and temperature to anticipate. These are all pretty much accelerated use conditions. High temperature retort packaging using that 121 degrees for 2 hours. That's going to be important for those type of applications. Whereas, if you just anticipate room temperature use, those would be well exaggerated conditions to which you wouldn't want to, subject your material or your packaging to when it's not needed. So then you would subject obviously to a 40 degree or 240 hour migration. So considerations for analytical testing that I think are going to be important. Obviously, the mode of testing selected will be determined based on the finished form of the food contact article, the conditions to which real world or real food is contacting the article, and the time and temperature limitations for which the article as well as the simulant will be able to withstand. You take, for example, a multi-layer film, maybe it's a retort of in nature, and you have to use a 95% ethanol. You're not going to be able to create a pouch and put those into an autoclave or a retort oven at that temperature to withstand. So we would use a migration cell. So there's all different modes of testing to be considered when kind of designing and performing the analytical testing. Once the exposure period has elapsed or finished in a way, or removed from the chamber, I think, so then the extracts have to be analyzed, right? So depending on the technique employed and the particular substance you're trying to detect, you may need to work from one stimulant into another stimulant or extract or concentrate in a way to get to lower LODs. So these are all different ways to consider or think about in terms of how you would prepare an extract for additional analysis. And then, I think when talking about the analytical approach or techniques to determine your targeted migration, really will depend on volatility of the substance. If it's very volatile, maybe gas chromatography will be implemented, or headspace analysis. I think also the polarity of the substance. Highly polar compounds tend to be tend to have a better separation or resolution on LC and detectable in a sense. Also, if they're thermally labile compounds, you probably want to run those by LC because the GC inlets would be too hot and extensive to degrade the compound. Also, nature of the food and the food stimulant, whether it's aqueous or fatty, will take into consideration how we would extract those out and how we'd actually prepare those extracts for those particular techniques. If it's elemental in nature, ICP, analysis is kind of the go-to for that. And then obviously if there's any knowns or unknowns, if you're looking for targeted versus untargeted analysis, whether it's using high resolution instrumentation to resolve co-eluding peaks, which again in extracts can be there could be a lot of peaks from those plastics or adhesives that you'll see. So really getting good high resolution separation is going to be important. Yeah, so what is non-intentionally added substances? I think really it kind of is self-explanatory in the sense of they're really, well, I go back here. I think there's really two main goals to identify when you're looking at NIAS, and I think those questions really are that need to be answered are what are the substances being detected, and at what quantity are those substances being detected in those extracts? If we want to define what NIAS really is, well, at least under the EU regulation, they have it defined as impurities in the raw materials used to make up those materials, reaction intermediates introduced in the production process, or degradation reaction products not intended to be part of the final material. These substances can be predictive, so knowing again the raw materials that were utilized, the manufacturing process, any possible degradation from either the raw materials or the polymers in themselves, or the materials that you're utilizing is of importance. So that way we can make NIAS a little bit more predictive in a sense, and not just truly unknown. Looking through the hourglass there. So if it is truly unknown, though, you do have to consider that the techniques employed, there's good trained analysts that are able to do this, able to match, libraries, but not only library matching, also to be able to elucidate structures, based on mass fragmentation, fingerprinting, and as well as the molecular weight of the compounds that were derived. These methods are usually longer in order to acquire appropriate data and require great separation or resolution to ensure you identify or any co-eluding peaks in the chromatography. I think it is important to correctly identify unknowns and confirm their identities using reference standards. So it's very important, if applicable, if you can get those reference standards, obviously. I do want to say that NIAS is really, it's not a catch-all for performing your due diligence. The substance, you may have substances that really aren't able to be detected by a certain technique. If they're not ionizable, you won't see them by mass spectrometry. That's where you may use different techniques like UV-Vis. So really, understanding the scope and who's doing testing and what techniques they're using is going to be important in identifying what true NIAS would be. I think it's also important to understand that it is semi-quantitative, like I said, and there are limitations even at at what limits of detection you're able to determine those. And there's a hard difference in how the toxicology would pan out in terms of structure-based versus toxicological data, and coming up with your margin of safety. So recycled materials. This kind of goes hand in hand with NIAS in a sense, because again, you may have different impurities that aren't intended to be a part of those. Obviously, I think until we figured out a way of inhabiting another celestial body in our solar system, I think it's going to, I think we need to have this responsibility to have a circular economy in mind, in a sense, and develop sustainable products, for its packaging. But at the same time, I think, in terms of recycling, we need to make sure that we're not sacrificing the safety as well as the quality of the packaging, so that way that food can maintain those proper shelf lives, and ensuring, again, like I said, the purity should be as equivalent as those virgin materials. The risks for using recycled materials include, I'd mentioned NIAS, right? Those degradation products are any of the concern in terms of impurities. Cross-contaminated chemicals from non-authorized materials. So, if you have PET that was used for non-food contact use, or a paperboard paper that that may have not been used for actual food carton or something along those lines, you may actually get cross-contamination of those uses, because some substances, obviously, they're in there, may not be authorized under those 21 CFR regulations or some other global legislation. Polymer degradation, obviously, over more and more mechanical and chemical recycling, you're going to get scission of those long chain polymers, creating voids, and obviously adding additional compounds that could possibly be contained within those polymers at the recycled materials at the end. It's also going to impact quality and reducing the physical and mechanical properties while increasing shelf life of the food. Here we have the process at which the FDA have a volunteering process for recyclers to provide them with letters of no objection. It's really a surrogate contaminant testing, to basically evaluate its safety on the process itself, not on individualized or batch testing of the materials. The testing protocol really works as follows. You kind of come up with a cocktail of materials, all the way from volatile, non-volatile, polar, non-polar compounds, metal elements, things like that, and you screen those elements. Well, essentially, you make the material, like a mostly virgin material, absorb them or condition them at 2 weeks at 40 degrees. And then after that absorption, the flakes are then analyzed to determine for the concentration, the residual concentration of those substances, immediately after. Then those flakes are decontaminated by subjecting them to the recycler's process, and then remeasured again to basically measure the efficacy at which the process was able to remove those intentionally added contaminants from that cocktail. But if we think outside of just what the FDA allows in terms of, again, as a voluntary process, I want to make sure that, I think it's more important to understand or have a QCS in place, really to evaluate and characterize materials for food contact use. I think the two main factors that should be assessed are content of hazardous substances and substitutability of virgin materials, or the substitutability of recycled materials for their virgin materials. It is our recommendation, I think, to look at the chemical, structural, and physical properties as a whole. There might be many unknowns in the recycled material, and many of these unknowns, could have once been actual added, adjuncts like plasticizers or antioxidants. Once, again, which had functional use then, but now have no functional use. But those, in a sense, can also form, peroxides and radicals, which could, easily increase the rate of polymer degradation. They may have reactive functional groups that can cause hydrolysis or oxidation, or any unwanted cross-linking of the polymer backbone. Again, I think understanding the full scope of, what your material is from all three of these properties kind of helps, understand that you're going to have the same material that's going to keep your product good for over its course of its shelf life. And real quick on exposure assessments, I know that we're getting pressed for time here, but the FDA establishes what's called the estimated daily intake, or an EDI, of a substance migrating from its packaging into specific types of foods. And these can be calculated using this formula here. The estimated, or the default assumption is that people, a human adult of 60 kilograms will consume about 3 kilograms of food per person per day. I think when you're talking about an infant, it's 900 grams of food. per person per day. So there's different ways to look at this. If, you know, again, if you're looking for an FCN for submission for an infant formula or human milk versus what you would for, you know, adult use or consumption factors there, taking into account who's utilizing it and their weights and criteria and dimensions. In essence, you also, I think it's important to understand is that under the FDA approach, there is what's called the consumption factor, and it is used to describe what fraction of the daily diet is expected to contain specific packaging materials. Kind of represents the fraction, I guess, or the ratio of the daily consumed packaged food that is packed in certain packaging materials. So again, if you're, you know, if you have different, you know, polymers or, you know, different, you know, materials all themselves, you know, metal, glass, plastic, paper, that where an additive may be utilized within those materials, that consumption factor goes into play because then, you know, you kind of spread it out in terms of how it can be utilized. It's also important to, you know, include food type distribution factors based on, you know, again, the materials and how much a particular food type is utilized with those materials, whether it be, again, like I said, metal, plastics, glass, so on and so forth. There's an actual factor that goes into play there and could be applied to the different migration concentrations found in those extracts to eventually formulate your EDI. And now, if there's multiple uses of this substance or authorized uses, either by 21 CFR, another FCN, or in a TOR somewhere, the FDA does have a database of what they consider cumulative estimated daily intakes. That'll need to be calculated and adjusted and understood for an exposure assessment, again, for already authorized uses of a substance or material. And so we have a case study here. This was one in which, you know, I think is good to talk about because really, I think oligomers are one of those that form predictive NIAS. You know, allow you to really draw out the possible structure conformations and, you know, measure the molecular weight distribution of, you know, what's in the material. So we had an inquiry where, you know, someone was trying to get, you know, an understanding of what the oligomeric fraction was that was leaching in from their polymer. And so what we decided to do was, you know, what you need to understand is if there is a mass distribution, you have to be able to fractionate out those and quantify those mass fractions as a ratio in order to understand, because each one of those mass fractions or distribution species of the oligomers may have a different propensity of migration. So if we don't do that, you know, and we use oligomers as a, you know, as a total, then we may miss something or underestimate the exposure for those oligomers. So what our approach here was what we did is we extracted with a suitable solvent the oligomers that were less than 1,000 Daltons, separated those by size exclusion chromatography, and then characterized those by high resolution mass spec. A migration simulation was performed using ethanol solutions and on the food content material, followed by a target analysis of those identified oligomers. In conclusion, it was determined that the oligomers were detected in the food stimulants, but results were found to be below the toxicological threshold. We have another case study here where, you know, there was a novel technology that was used. Basically, we were looking for, we needed to look for silicon concentration in the in basically a 50% ethanol, which is, you know, stimulant for infant formula. And this had to be done at 100 degrees, you know, again, over the boiling point in 10 days. We were able to provide gas tight vessels for this, PTFE vessels, place plaques into those vessels, and then be able to really get to the 100 degrees over the course of the full 10 days. Now that they were ethanol solutions, this makes it more difficult bringing up the background levels in the ICP-MS, so we weren't really able to get to those the insignificant level of that 25% 24 part per billion because of the ethanol solution. So what we had to do is we had to remove the ethanol and then dilute back into water and then reanalyze this by ICP-MS. All in all, while performing validation studies, getting our particular recoveries and things like that. I think in conclusion, since we were able to remove the organics, use PTFE instead of glassware, we were able to achieve those LODs, and the extracts were shown to have typical silicone, but the CEDIs were well below levels deemed insignificant. And so for our case study, our last case study here, I know we're kind of running out of time, so I just wanted to kind of get through this. We do get asked quite a bit of time, a lot of times on undesired transfer or what's called setup migration. This is, ink components that may, be on the opposite side of the food contact side that are stacked or rolled that could transfer to that food contact side. Basically, our approach here is that we apply a 1 kilogram weight over the course of 10 days. After that, the unprinted layer is placed into the migration cell, contacting the sema under time and temperatures of anticipated use. And then the solution is analyzed by an appropriate analytical technique to identify either known or unknown contaminants. We have had several issues here too, even when low migration inks have been, determined to be low migration, that there was a transfer of things like acrylates to the inner surface and can be above those acceptable levels that would deem it, criteria for margin of safety anyway. And as I kind of just in the discussion here, we wanted to provide you with a degree of additional services that we do offer. And I think we did kind of talk about polymer ID and characterization a little bit today, but we do provide other integrity testing in terms for seams and bubble emissions. We do shelf life and stability testing here at Eurofins. We can determine the opacity of the materials, make sure that there's no light sensitive compounds that would be affected, from the, in terms of the packaging to the product. Also, many of our, as we discussed today, it could be their targeted or non-targeted migration analysis. We have many of the techniques utilized between high res and low resolution chromatography and mass spectrometry to be utilized.
All right, perfect. Thanks so much, Drew. We do have a few questions in the chat. We have a few minutes here. So the first question, what is the difference between the migration testing needed by the FDA versus what is performed in the EU?
Yeah, so really, with the FDA, you're talking about unauthorized uses. They have very similar ways in a sense of conducting those in terms of the accelerated conditions. They may have slightly different conditions. The JRC may recommend certain conditions for how hot fill gets utilized, more so like at 70 degrees, and then using worst case times to simulate that, as opposed to the FDA. When you use hot fill, you may fill it to a certain temperature at that temperature, and then lower those temperatures to extended storage conditions. So there may be subtle differences there. Obviously, I think a lot of the times people also confuse total non-volatile extractives tests with migration tests, and these are not. Those are strictly just quality tests or characterization of already authorized polymers. So just keep that in mind, that you want to make sure that the materials that you're using now are authorized for their intended use. It's always based on a positive list. And then going from there, defining if you already have authorization or not. And, we can always help with that.
Okay, perfect. Another question, do I need to perform migration testing on my film if each of the layers are compliant to 21 CFR regulation?
That's a good question. I think, I think it really kind of depends. There are two sections under the 21 CFR, 177.1390 and 1395, that, you know, one really for kind of retort applications and the other for really just multi-layer laminate films. That, you know, you can, as long as you have authorization of those substances, or, you know, whatever materials that you're using, typically that is good enough. There is no additional testing that's needed. However, you know, I would say this, you know, adhesives, right? They need to have certain barriers. So if you're using an adhesive or a tie layer, you may need to try to identify if it's actually migrating, because you need an actual functional barrier to be utilized. And the only way to really do that is, you know, through migration assessments, either through those calculations or migration testing. So it could be a possibility. I would say it's definitely, it's one of those things that's, you know, it's product to product based. So.
All right, perfect. And then we have a minute left. Let's do one more quick question. If we sell different sizes of the same container, can we perform testing on a single size, and what size would that be?
Yeah, certainly. So again, you'd probably want to use something where, you know, usually smaller sizes will indicate that you'll have more exposure in terms of the food, depending on what the food is too. You know, the surface area, you know, if it's a solid food, we'd probably want to, you know, identify that. But typically, we can test to one surface area to volume ratio. We just want to choose the worst case in that sense.
Perfect. And then one more quick question.
Yep.
For paper packaging, is the finished packaging what is tested for migration, or the final film in the packaging?
For paper packaging, sorry, can you repeat that question one more time?
Yeah, absolutely. For paper packaging, is the finished packaging what is tested for migration, or the final film in the packaging?
I would say, now, if I'm having to assume here, what you mean is like if there is a barrier film that is on one side in contact with the food, as opposed from the pack or the paper itself, you would want to test the final article for what would have the propensity to leach into the simulant. That way it takes into account what could possibly transfer from the paper, as well as possibly, you know, again, an adhesive or something that's utilized in between the layers, or obviously the film as well. Now we can also use the film as a control to identify what is particularly coming from the paper itself versus what would be coming from the film. So there's many ways to look at that, but obviously you'd probably want to do the final form that would be in contact with the food.
All right, perfect. Well, thank you so much. Just want to say thank you both to you, Drew and Trish, for today's presentation, and a big thank you to everyone who's attended. Please feel free to reach out with any questions, and we would be happy to connect further to discuss this important topic. This now will conclude today's presentation. Have a wonderful day.